你不着急啊，到时候超点时间也无所谓的，好吧？
好的。
反正
对，我听你昨天说完，然后我把 PPT 稍微删了一点，就是删了大概2页纸的。
你这个正好做个准备，到时候你到那边理的话，对你给他讲的话就会好讲一点。
就是相当于自己已经整理过一遍了。
对，他会问你很多问题。
对，那个李永南老师好像也是叫我28号早上去见他一下。
你上次说 strict nav 如果有一个 section 它就是 ample 的是吧？
对，至少3维的是对的。对，
不需要什么不需要什么 Serrano 的那种 K 加的。
不需要，不需要，应该。对。
所以说特别的，如果它是 big 的话，那么它就是 ample 的是吧？
对 big 就非常更好了，就是基本上
big 是不是高维也对啊 ？strict nav 加 big。
base point free 可以用吗？如果是
nav and big 不一定 base point free。nav and big
可能减掉 kx a 减 k。
I don't know。3维是为什么
？3维是因为我算一下啊，
要有阳针吗？还是什么？还是不用？如果有一个 section， 曲面是
好像等一下，3维好像也要。
K
你这么一说，好像确实3维可能也要加 k 的。对。你这么一说，3维
的 surface 是 OK 的。
surface 对 surface 因为你用是不是 Hodge index 就可以了呀？Hodge index
对，就是你 divide self intersection intersection， 我也不清楚啊，但是它可能
d 平方大于
对，有点麻烦。
d 平方大于0。d
OK。因为你现在不用考虑了，我们准备开始
懂了
啊。虽然人不是很多。Okay, so today I'm very happy to introduce Dr. Zhong Guolei from IBS to give the second talk on strict nav divisor on singular varieties. Okay, you may start.
Okay, so today we continue to discuss the strict nav divisors. Okay, so today I will mainly we will focus on the threefold case. Okay, so first we still review some previous results, and then I will state our second main result, and after that I will introduce some key ideas for the proofs, and finally I also ask some open questions. Okay, so today's talk is based on the joint work with Zhong Wang. Okay, so we still start from a projective variety X over the complex number C. Okay, so a Q-Cartier divisor L is said to be strict nav if it has positive intersection with every integral irreducible curve. So last time we focused on the case when L is the anti-log canonical divisor and show the two theorems. So first, we show that if this minus k plus delta is strict nav, then such X is rationally connected. And another result is in particular on the threefold case. Okay, if this minus k plus delta is strict nav, then we show that this minus k plus delta is ample. In other words, this x delta is final type. Okay, so now today we will study the Serrano's conjecture and mainly on the threefold case. Okay, so let's recall that the Serrano's conjectures predicts that on a smooth projective variety X, and a strict nav Q Cartier divisor LX on X. Sorry, maybe here I need to drop out the Q because smooth is always factorial. Okay, sorry. So a strict left Cartier divisor Lx, then this Kx plus TLx is ample for sufficiently large T. Okay. So first, I will give a remark from the viewpoints of the Cone theory. Okay, so it seems a bit dense, but I will explain in a more detailed way. So we denote by this n lower 1x the space generated by real 1 cycles modulo numerical equivalence. And the numerical class of every Cartier divisor, which usually we denote by this as the n upper 1x, okay? So up to a multiple on x is in one-to-one correspondence with the hyperplane of n lower 1x along a perfect pairing, okay, passing through the origin. So applying the Kleiman's criterion, we know that a divisor L is ample if and only if the Mori cone is strictly contained in the half space L greater than 0. Okay, this is by the Kleiman's criterion. Okay. So, if we denote by this HL the 0 locus of the hyperplane defined by L, okay, then the Cyrano's conjecture is equivalent to the intersection of this HL and HKX. The intersection is disjoint with the Mori cone. Okay, because you can see one direction is easy because if you find an extreme ray in the Mori cone alpha such that this L times alpha is 0 and the Kx times alpha is 0, then this Kx plus TLx times alpha is still 0. So this means that if this is not disjoint, the intersection is not disjoint with the Mori cone, then this Kx plus TLx is not ample. In other words, the ampleness of Kx plus TLx will forces these two guys to be disjoint. And on the other hand, if we have already known this HL intersection with HKX being disjoint with the NE bar X, then by using the Cone theorem, we can also show that Kx plus TLx times alpha is positive for every ray alpha in the Mori cone. Okay. So the inverse direction needs the Cone theorem. Especially we need the lower bound for the negative extreme ray. Okay, so now we review some previous results. So first, Cyrano proved in 1995 that his conjecture has a positive answer for Gorenstein surfaces and the abelian varieties of any dimension. And also by the two works, Cyrano's single authored work in 1995 and Campana, Chen, and Pitnell in 2008, that the Cyrano's conjecture has a positive answer in threefold case, smooth threefold case, unless X is Calabi-Yau with such that this Lx times the second Chen class is 0. So here we will mainly generalize this theorem to the singular case today. Okay. So when X is K-trivial, so in this this means that the canonical divisor Kx is numerically trivial. Okay. Then Cyrano's conjecture predicts that every strict left divisor is ample because you can see in this form we know that if Kx is numerically trivial, then if Lx is strict left, then it implies that Lx is ample. Okay. So so when X is K-trivial, Cyrano's conjecture predicts that every strict left divisor is ample. And for the remaining case in dimension 3, so you can see from this theorem, the remaining
sorry.
Oh, okay.
So when X is K-trivial, then Cyrano's conjecture is the weak form of the Neff abundance, right?
Yeah. You can see like this, but
the Neff abundance
Neff abundance
is Cyrano's conjecture when K is trivial. Can we?
Yes. By the I think by the base point free theorem, I think by the base point free theorem, it defines a fibration to the downstairs and the strict. If the abundance is true, then the strict leftness will imply it is ample. Yeah.
Okay.
Yeah.
Let's see.
So for the remaining case in dimension 3, so in other words, you can see from this theorem, the only remaining case is the Calabi-Yau with the Lx times C2 is 0. Okay. In this case, Liu and Savadi had some further progress recently. Okay. So they show that if X is a Calabi-Yau threefold with the third Chen class not vanishing, and D is a strict left divisor with the numerical dimension not equal to 1, then they show that D is ample. So for the proof, they utilized the Riemann-Roch formula and to discuss something. Yeah. Okay, so later on, Liu and Matsumura consider the a weak form of Cyrano's conjecture in fourfold case, but they only consider the K trivial fourfold case. Okay, so consider X is a K trivial fourfold and L is a strict left divisor. And they show that if such L has a section, in other words, the kappa L is non-negative, okay, then L is ample. L is ample. But in general, if we don't, if we drop the K trivial condition, then this is still unknown. Okay. Moreover, if the numerical dimension is not equal to 2, then they can show that such L is ample. Okay.
Wait a minute. I remember the net abundance holds true when for the Calabi-Yau threefold or high dimension, when the L has a section, right? If L is a left divisor and it has a section, then it is semi-ample. Is it? I remember. Okay, so
I think in the Calabi-Yau threefold case,
because
you have
a section, then you can use the proof of the base point free string theorem, right? Okay, you can check later. Okay, you can go.
Okay, but yeah, this according to their theorems, it seems that there are some gaps. I'm not sure. Let me see. Yeah. So maybe we can discuss this at the end of the talk because I also ask a question here. So now we ask the singular pair version of Cyrano's conjecture. So consider this X delta as a projective KLT pair. Okay, so this means this X is a projective variety and the X delta has only KLT singularities. And we give a strict left Q divisor Lx on X. And we ask whether this Kx plus delta plus TLx is ample for sufficiently large T or not. Okay. So the lower bound of such T in terms of the Cartier index of Lx, okay, is another interesting problem. But here we only consider arbitrary sufficiently large T. Okay. And also the KLT singularities might be replaced by LC singularities, at least for the surface case, LC case is true. Okay. And also as observed by Haidong Liu, the singular version of Cyrano's conjecture in dimension 3 will imply the Campana-Peter-Nels conjecture in dimension 4. So Campana-Peter-Nels conjecture means if the anti-canonical divisor minus K is strict left, then this X is final. In other words, this minus K is ample. Okay. Okay. So as I just mentioned, the log version of Cyrano's conjecture has a positive answer on surfaces by studying the generalized pairs. So this is a joint work by Jing Junhang and Wenfei Liu in 2020. So if X delta is a projective LC surface pair and Lx is a strict left Cartier divisor on X, then they show that this Kx plus delta plus TLx is ample for every real number T. Okay. So this is a corollary by studying the generalized pairs. And note that the log version of Serrano's conjecture is still widely open even in dimension 3. And the above theorem on the surface case can be further extended to positive characteristics by running a similar strategy. And finally, motivated by the joint work of Campana, Chen, and Peter Neal, we can give a partial answer to the singular pure version of Serrano's conjecture in dimension 3. But unfortunately, the pair version is still unknown. Okay, so now we state our main result. Okay. So note that we will treat the Cordaro dimensions kappa greater than 0, equal to 0, and negative separately. Okay. So now we start from a normal projective threefold with only KLT singularities X. And we denote by a strict left Q Cartier divisor Lx on X. And we suppose that one of the following conditions holds. So first, if the Cordaro dimension is greater than or equal to 1. The second thing is if the augmented irregularity is positive. Okay. And either X is Q factorial or X has only canonical singularities. Okay, so in general, we only assume this X has only KLT singularities, but in the second part, we need to further assume either X is Q factorial KLT or canonical singularities. And the third point is the Cordaro dimension is 0, and X has only terminal singularities, and the second Chen class has non-negative intersection with this strict length divisor Lx is non-zero. Okay, so this is the case for the kappa x equal to 0. And finally, is about the uniruled case. Okay, and uniruled case we need the Gorenstein canonical singularities. Okay, so these conditions is to make sure there does not appear any small contractions when we run the minimal model program. Okay, so the first, the second, and the third part, we can deduce the ampleness of K plus TLX directly, okay, by some calculations. But for the for the point 4, when X is uniruled, we need to run the minimal model program. Okay, so I will explain this later on.
Okay, I have a question. So in your condition 3, you said the intersection is non-zero.
Yeah.
Is it true that if it is non-zero, it isn't greater than 0, or it is?
Yeah. If this is non-zero, then this is greater than 0 by I think by Mielka's pseudo effectiveness of C2.
Okay.
Yeah,
Okay,
yeah, this is positive. All right.
Okay, I see.
Okay, so now so there are too many conditions here, but maybe we can give a clean corollary here. So if X is a Q factorial Gorenstein terminal projective threefold, and there is a strict left divisor Lx here, then we can show Kx plus TLx is ample for sufficiently large T, unless X is weak Calabi-Yau and such that this Lx times C2 is 0. And note that, so you can see, oh, sorry. So you can see every case will be included, okay, except for the kappa x equal to 0 with Lx times C2 is equal to 0. Okay, so there is a distance from the kappa x equal to 0 with, and the numerical trivial k, because if this kappa x equal to 0, but k is not numerically trivial, then this means that kx will be numerically effective. Then by some lemma, we can show it is ample. So we reduce to the X is weak Calabi-Yau and the zero intersection with LX with C2. Okay. Note that this C2 is a birational second Chern class. Okay. So I will introduce some notations, some symbols and notations here. So the augmented irregularity Q0x is defined as the maximum of the irregularities Q, where this X tilde to X runs over all the finite quasi-tau covers of X. Okay, so you can see this definition in a paper by Nakayama and Zhang in 2010. Okay, so this Q0x appears in our second condition. Okay, so this means not only we consider the irregularity Q, but also we need to consider all the quasi-tau covers of such X. Okay, so this is much weaker than the positive irregularity. Okay. Okay, then we say that projective KLT variety is weak Calabi-Yau if this Kx is Q linear equivalent to 0 and the augmented irregularity is also 0. Okay. So we reduce to a very, very special case. Okay, so Kx is 0, Q0x is 0, and C2 times Lx is 0. Okay, so we are not able to deal with this case. For the remaining other cases under this condition, Serrano's conjecture holds true. And also the birational second Chern class, this C2 is defined by its resolution. Usually you can regard this as one cycle as the push forward of the usual second Chern class from its smooth model, which is minimal in codimension 2. Okay, so this is introduced by Shefford, Barron, and Wilson in 1994. Okay, so this is our main corollary that X for the Gorenstein terminal case. Okay, so in the following we will consider the proof, but we shall deal with the proof one by one. Okay, case by case. Okay, so but before that, as I just mentioned yesterday, there are some different versions from Q effectiveness to the ampleness. Okay. So let's recall the two important lemmas here. So first, the first lemma, I call it the Q factorial pure case lemma. Okay. So this is from the effectiveness to the ampleness when this X is Q factorial. Okay. So we start from Q factorial normal projective KLT threefold. And Lx is a strict length Q Cartier divisor on X. And we suppose that there exists some linear combination ALX plus BKX, which is numerically equivalent to a non-zero effective divisor. Okay. Then KX plus TLX is ample for sufficiently large T. Note that this is the most general form if we assume X is Q factorial. Then we don't need any other conditions. So we only need some linear combination ALX plus BLX is numerically effective. And also note that we don't have any requirements on this A and B. Either A equal to 0, A smaller than 0, negative, positive, doesn't matter. Okay, we only require some linear combination is numerically effective. Then we can show that this KX plus TLX is ample. Okay, so this form, this is the most general form we can develop. And there are some other versions if we drop the Q factorialness, because in general, especially if you use the junction, then in this situation, Q factorial seems to be very important. However, if we drop the Q factorialness, then there is another way. We take the Q factorial terminalization, but in this case, it may affect the strict leftness of this Lx when you pull back to its terminal model. Okay, so I will give another version we call the non-Q factorial case. Okay, so this is not in the general form. Okay, because we need to assume some further conditions. Okay, in general, the general KLT case with the non-Q factorial x, we are still not able to develop the most general form. Okay, so let's see the condition here. So still with the same condition as in lemma 1, except for the Q factorialness. Okay, so in this case, we also consider the pair case. Okay, so we let X delta be a projective KLT threefold pair. And still there is a strict left divisor LX here. And we suppose that one of the following conditions hold. There are two conditions. So one of the conditions hold is enough. So first, LX is numerically effective. So note that here in lemma 1, we only require any linear combination is numerically effective. But if we consider the non-Q factorial case, then we require LX is numerically effective. Or we can let this delta, another condition is delta is 0. We consider the pure case. And in this case, we assume X has only canonical singularities. Then we use the same condition as in lemma 1. Okay, so some linear combination is numerically effective. Then in this case, we can show that Kx plus delta plus TLX is ample for sufficiently large T. Okay, so note that the difference between lemma 1 and lemma 2. So if we drop the Q factorialness in lemma 2, then we need some further conditions. Either this LX itself is numerically equivalent to a non-zero effective divisor, or we require such X has only canonical singularities. Okay, then we can show this Kx plus delta plus TLX is ample for sufficiently large T. Okay, so,
sorry.
Okay.
In lemma 2 second condition, you assume delta equal to 0 and X has canonical singularity. You assume canonical singularity because you want to take the Q factorial model right here.
Right.
To control the exceptional divisor.
Yes, right. You are right. Yes.
But why you need the delta equal to 0 here?
Because when you apply the adjunction, when you restriction, for example, this numerically equivalent to sum of Fi, right? Some components Fi. Then, for example, if you restriction to some components F, then a Kx plus F restriction to F is okay. But this delta restriction to F will have some problems.
Okay, I might have some multiplicity, not.
Yeah.
I guess if you assume X delta has canonical singularity, then it is still okay. You still can control it anyway. Okay, you can go.
Yeah. Maybe we can continue to consider this case because initially I'm only able to deal with lemma 1, but later on when I consider this case, then I think these two cases can be added. Yeah, maybe. So I just say this is not in the general form. Yeah, maybe we can further develop this lemma. Okay, so now we should prove our main theorem case by case. Okay, so first is about the positive cordillera dimension. Okay, so for a positive cordillera dimension is very clean. Okay, in this case, we can prove in the most general form. Okay, so if X delta is a projective KLT threefold pair, and suppose the log cordillera dimension kappa Kx plus delta is greater than or equal to 1, then we can show this Kx plus delta plus TLX is ample for sufficiently large T. Okay, so note that there are two key points. So first, this Kx plus delta plus TLX is strictly enough for sufficient large T. So this is true for any projective KLT pair X delta. So this is by the Kohn theorem. You just control the kx plus delta negative curves, okay, by this Lx. So once this Lx is strict enough, then we can easily show this is also strict enough for sufficient large T. And then the second point is to show that kx plus TLx is numerically equivalent to an effective divisor by applying a result of Lezik and Peter-Nel. Actually, they show they can further show this is numerically equivalent to a semi-ample effective divisor. Actually, this is numerically equivalent to a semi-ample effective divisor. Okay, so then we apply the base point free theorem. We can show this is ample. Okay, so this theorem is not easy. It's not hard to prove by applying the previous result, but from our viewpoints, we try to generalize it to the any-dimensional case. So as a high-dimensional analog.
Sorry.
Okay.
So your assumption is that kx plus delta has at least one-dimensional sections, right? Then is it true that if a divisor has a one-dimensional section plus a strictly enough divisor, is it possible that it still has a section, or there is a counterexample here?
You mean strict enough divisor plus
some very plus a one-dimensional, yeah, effective divisor.
I see what you mean.
Also, maybe this part is difficult. I have a question on your first part. You applying the Kohn theorem, but the k negative part, I forgot about the delta here. Okay, so the k negative curves, there are possibly infinite many k negative curves. So for each curve, you need to get one t, right?
No. You can find a union T. I think this T, for example, if we assume this Lx is integral, because you can always replace this x by a multiple, right? Then I think this T should be, the lower bound should be 2 times dimension x. Because by the calculation, the
because of the
part,
binary break. Okay, I see.
Yeah. You are right. Yeah, you are right. So this T is union T. Okay. Okay, so let's continue. So as a high dimensional analog, we can show the following proposition. Okay. So this is in the high dimensional analog. However, so I'm sorry for too many technical conditions, because in the high dimensional case, we are not able to deal with the KLT case, but canonical case is clear. Okay, so if X delta is a projective canonical pair, and the Lx is a strict enough Q divisor, and we suppose the Ithaca dimension, some linear combination, okay, is greater than or equal to dimension X minus 2. So this is quite clear. This is quite similar as the conditions here, because in the spherical case, this is just a 1. Okay. Then we can show this kx plus delta plus TLx is ample for sufficiently large T. Note that here we also we also put the Lx here. So this is more general. Because in this case, we just let this be equal to 0. Okay, but in general, we only require this is a linear combination has a the kappa is no less than dimension x minus 2. Okay, then someone will ask why we give such conditions. So the point is that in this case, we can reduce to the general fiber of the Ithaca fibration, and the general fiber is the surface case. So we just reduce to the surface case. Okay, so the surface case, we can apply the Serrano's theorem, and then by some calculation, we can show the whole thing. This is the ample. Okay, so this is a proposition we generalize, but we are not satisfied with this proposition, so we didn't put it into a theorem, just a proposition as a first try. Okay, so this is the case for the positive quadratic dimension on the threefold case. Okay, so now next case is the positive augmented irregularity. Okay, so this is somehow related to the Albanese map. So we develop the technical result, which is first proved by the Campana, Chen, and Peter Nail, but we generalize this technical result to the singular case. Okay. So we consider a projective KLT threefold pair and a straight Q Cartier divisor LX. And we suppose that the irregularity is positive. Okay, so first we consider the irregularity, and then we consider the augmented irregularity, just to take the quasi-tau cover. So there does not contain any technical parts. Okay, so we just first consider the Q positive. In this case, we can show that Kx plus delta plus TLX is numerically effective. Okay. So if this Q is positive, then we can show Kx plus delta plus T is positive, TLX is positive, numerically effective. Someone will have some high dimensional analog as observed by Peter Nail and Lezik. However, they assumed Kx plus delta is pseudo-effective, but in our case, we don't assume such condition, okay, because we have already have such strong conditions, strict deafness. So we don't require Kx plus delta is pseudo-effective, okay. In some other papers, they may assume Kx plus delta is pseudo-effective by running the minimum model program. But here we don't need this. Note also that the proof for the proof we need to use the Fourier-Mukai transform to show that this Kx plus delta plus TLX is numerically effective. Okay, so but this is too technical, so I will skip the proof here. And so by using this technical result, we can show our main theorem in the case Q0 positive. Okay. So we consider a projective KLT threefold with the augmented irregularity Q greater than 0. And there is a strict Q divisor LX here. And suppose that either X is Q factorial or X has only canonical singularities. Then we can show Kx plus TLX is ample. Note that this condition Q factorial or canonical singularity is just because we need to apply the previous our lemmas from effectiveness to the ampleness. Okay. So I will give a short proof here. Okay, you can see we pass this X to the quasi-tau cover X prime, such that this Qx prime is positive, okay, because according to the definition, okay. And by this technical result, we can show that our Kx prime plus TLX prime is numerically effective for some sufficiently large T, okay. And if X is canonical, then so is X prime by a result of in the Collar-Morris book, okay. Then in this case, by our previous lemma 2, for the non-Q factorial case, we can show the Kx prime plus TLX prime is ample. Okay, so so the downstairs is still ample because this is the finite pullback. And another case is the Q factorial case. So if X is Q factorial, then we know the Kx prime plus TLX prime is numerically effective. So the push forward Kx plus TLX is weakly numerically effective. Sorry, I don't want to intend to introduce the weak numerical equivalence, but you can by a theorem proved by De-Qi Zhang in his paper, if X is Q factorial, then the weak numerical equivalence is equivalent to the numerical equivalence. So since X, we assume X is Q factorial, then the downstairs Kx plus TLX is still numerically effective. then we are done. Okay, so so this condition, I don't like this condition. I hope that we can by studying the non-Q factorial case in our lemmas, in our previous lemmas, from the effectiveness to the ampleness, we can drop these conditions. Okay. So in the augmented reliability positive being positive, in this case, we can also show kx plus tlx is ample if x is q factorial or canonical singularities. Okay. So this is the second case, q0 being positive. Okay. Okay, now let's continue. So the third case is the kappa x being 0. Note that we don't finish the proof for the whole case kappa x equal to 0. Okay, there is a remaining case, the Lx times C2 equal to 0. We are not able to deal with. Okay, so in this case, if we assume Lx times C2 not vanishing, then we can show kx plus tlx is ample. Okay, so note that by our previous page, we can reduce to the case Q augmented reality vanishing. Okay, and also we may assume kx is numerically trivial. For otherwise, this kx would be numerically effective, and hence we are done by the previous lemmas. So we just assume kx is numerically equivalent to 0. And then by the abundance, we may further assume this kx is semi-ample, q linear equivalent to 0. And thus, this x is weak Calabi-Yau. Okay, so the abundance just follows from the paper by Nakayama or Gongyu. I think Gongyu dealt with the LC singularities. Okay. This is in a more general form. Okay, so on the one hand, we after passing x to its maximally quasi-tau cover in the sense of grab Quebec's Peter Nail. So this cover is too technical. So I just skip the definition here.
Oh, sorry to interrupt. You say you
okay.
take the maximum quantity, but your x is V Calabi-Yau, right? Kx Q triple.
No.
Then is torsion. Then you can take the
So first,
right?
You are right. First, we need to take the global index 1 cover. Then we further take the maximally quasi-tau cover, Galois cover.
You try to remove the abelian variety part, right? Then it is something like a strict Calabi-Yau, right?
Yeah. You can imagine like this.
So since abelian variety is simple, then you take the something called the universal cover or abundance closure, something like that.
Yeah.
Okay, then you
because the grab Quebec's Peter Nail, they study the tau fundamental group and its representation. So
I don't think you need this. You simply use the Fourier Bogomolov decomposition, right? See, this X has a quasi-tau lifting to a product of abelian varieties and Calabi-Yau varieties, right? That's all.
Yeah, but note that we need to study the abelianness of the linear representation. You know, the in the singular case, the hyperkähler part is fine, right? Because the hyperkähler the fundamental group is always the regular locus of its fundamental group is always.
I mean, why you need to study the fundamental group? You want to try to show this theorem, right? You want to show this theorem, then it is free to take the quasi-tau cover because you have no ramification divisor. So K is preserved by pullback. And for finite surjective morphism, the strict left divisor is preserved under pullback, right? By the projection formula.
Yeah. But then we need to show kx plus tlx is ample.
Yeah, then you upstairs you show it is ample. Since it is the pullback of finite pullback of ample divisor. A finite pullback of a divisor being ample implies the original ample, right?
Then how you show the in the Calabi in the upstairs this Lx is ample? Yeah.
Yeah, I think I say that then you can reduce this theorem
to
to
the
X being simply strictly Calabi-Yau. That's all. Calabi-Yau threefold.
But I think in Calabi, even in Calabi-Yau threefold, this may not be true. I think. I mean, you need the I mean you need
I know
condition.
you need this assumption, but everything.
Yeah. If we have already solved this case, then of course, yeah, you are right.
Okay, we can discuss this.
Oh, okay. Sure. Okay, so I mean, by passing this X to this maximally quasi-tau cover, I just need to use the result developed by the Grab-Quebec-Pinel that the linear representation of its regular local, the fundamental group of its regular locals always has abelian image. Okay. So on the other hand, the Miyaoka's pseudo-effectivity of this C2 implies as you mentioned, as Shen mentioned in the beginning, this Lx times C2 will be positive. Okay, then some further calculation will give this H1 non-vanishing. Okay, then if this is non-vanishing by a previous theorem with a few modification, we can show there exists a finite dimensional linear representation whose image is not abelian. Then we get a contradiction. So the problem, the point is that if this is not ample, then on the one hand, the finite dimensional linear representation of this pi1 X regular has abelian image. On the other hand, we can find a finite dimensional linear representation whose image is not abelian. Then we get a contradiction. Okay. So note that this is always true. This is always true on the Calabi-Yau manifolds, on the Calabi-Yau singular KLT singular Calabi-Yau varieties. Okay, but the second part, we need the assumption that Kx plus TLx is not ample. So we assume by contradiction. Okay, so this is one of the case when the Lx times C2 are not equal to 0. However, the Lx times C2 equal to 0 is not is unknown. Even in the smooth case, it is unknown. Okay. I think in the smooth case, the things will be more simpler. Yeah, as proved in Serrano's paper. Yeah. Okay, so this is a case for the kappa x equal to 0. So so finally, we reduce to the uniruled case. Okay, so we consider the uniruled case with Q augmented irregularity vanishing. So before that, we first record the following lemma. So this lemma just tells us that when this X is Gorenstein isolated canonical singularities, it does not have any flipping contractions, any small contractions when we run the minimum model program. So you can just observe the condition. If there is a birational k-negative extremal contraction, whose fibers are at most one-dimensional. Okay. Note that here we don't require it is an elementary contraction. In other words, this Picard number rho x can be equal to rho I plus 2 or plus 3. Yeah, we don't require this is an elementary contraction. So so the relative Picard number can be 2 or 3, may not be 1. Okay. But we require the fibers are at most one-dimensional. Then in this case, this lemma tells us that it is a divisorial contraction. Okay, so this is the composition of divisorial contractions, mapping the exceptional divisors to curves. Okay, and also in this case, the singularities on Y will not be worse. Okay, so in this case, since X has Gorenstein isolated canonical singularities. Y also has we can also show Y has only Gorenstein isolated canonical singularities. Okay. And actually, you can consider this as in the smooth case. So in the smooth case, by the Morris theorem, Morris theorem shows us the smooth threefold has no k-negative small contraction. Okay, and in this case, it should be the blow up of a smooth curve from downstairs. And in the singular case, still we have some similar conclusion. Okay, and this is the actually this is the simultaneous blow ups of smooth curves. Okay. Okay, so why we need the Gorenstein canonical with only isolated singularities? So note that when running the first step of the minimum model program, there does not appear small contractions. So now we should run the first step of the minimum model program. So first, some easy case. Okay, so final contraction to curve. So if X delta is a projective KLT threefold pair, and there is a string length Lx. Okay, suppose that the Picard number is no more than 2. Okay, so this is the case when X admits an elementary final contraction to curve. Okay, then we can show Kx plus delta plus TLx is ample. So Picard number 2 case is easy. Because in this case, we may assume Kx plus delta and Lx are not parallel. For otherwise, this minus K plus delta will be stripped length. And then by our main result last time, okay, then minus K plus delta will be ample. So in this case, we may assume these two guys are not parallel. Then we can construct a linear combination to be ample, okay, such that it is Q effective. So final contraction to curve case, this is easy. And the second thing is the final contraction to surface. Okay, so to surface case, still not very hard to deal with. So so in this case, we can still show Kx plus TLx is ample for sufficient large T. Okay, if there is an elementary K-negative contraction to a projective surface S. And for the surface case, the main idea is to construct a linear combination which is numerically equivalent to the pullback of an effective divisor from S. So we can construct an effective divisor on S such that its pullback is some linear combination. And then we show this is Q effective. And by our previous lemmas, this is ample. This is ample. Okay. Okay, so final contractions are not very hard to deal with. Moreover, we can generalize this theorem to the conic bundle case. Okay, so this is for the usage of the last step. Okay, so this means if this X admits an equidimensional K-negative extremal contraction to surface S, such that this Kx plus ULx is the pullback of some M. In other words, actually, this is just some AKX plus BLX. Okay, so this is the pullback of some effective divisors. Then we can also show this Kx plus TLx is ample. So in the last step, we just construct a series of blowdowns to curves, and followed by the last step is a final contraction to surface.
Sorry, then, is this simply because for this is simply because your M is ample, right?
May not be ample. Our M is just effective, I think. May not. I think. May
but
not
if
be.
it is not ample, how do you? Okay.
Yeah. If this is not, if this is effective, then we can show this is also numerically equivalent to an effective divisor, right?
Is it something like the pullback ample plus your LX is relative ample, right? because
LX is relative ample.
Then you
right.
use the pullback ample plus relative ample.
The idea you mentioned is has also been used in our proof, but I think not in this theorem.
But your M here is automatically ample, has to be ample. If it is ample, if K plus TLX is ample, your M here is.
But note that here this U is not sufficiently large. This is just a coefficient such that this is relative trivial.
Only effective, right?
Yeah. This is just numeric. This is relative trivial, pi trivial. Okay. This is because you can see if Kx plus Tx is ample, then it can never be the pullback from downstairs.
Okay, I see. Okay.
Yeah. Okay. So the rho here it plays is just something like A Kx plus BLX, the linear combination. It's the pullback from downstairs. Then we show this numerically effective, and then finally we show this is ample. Okay. But now we don't need this theorem here. Okay, this is just for the usage of the last step. And so finally, we since in our Gorenstein terminal case, Gorenstein isolated canonical singularities case, there does not have any. We don't have any small contractions. So except for the final contractions, we only need to deal with the divisorial contractions. Okay, so one divisorial case is easy. So if it is a divisorial contraction mapping the exception divisor to a point, then things will also be very good. Okay, so if there is a divisorial contraction such that the exception divisor is mapped to a point, then we can also show this is ample just by using some ramification divisor formula. And some calculations, then we can show the original Kx plus delta plus TLX is ample. Okay, so this case is also easy. So now we reduce to the following case: all the contractions, all the extremal contractions from such X are divisorial contractions mapping the exceptional divisor to curves. Okay, so finally we reduce to this case. So because once there exists some other type of contractions, then we can show Kx plus delta plus TLX is ample. Okay. So therefore we are left to show the following theorem. So if X is a Q factorial Gorenstein normal projective uniruled threefold with isolated canonical singularities. Also note that so far we don't need the uniruled in the previous final contractions and the divisorial contractions to point. Okay, but in this last step we need the uniruled is okay. And there is a string length divisor Lx. And suppose all the elementary K negative extremal contractions are divisorial. Okay, mapping the exceptional divisors to curves. Okay, then we can show it is ample. So this is the most technical and difficult part in this project. Okay. So I just give a main idea here, but I will try to simplify the idea. Okay. So we, for example, we start from a divisorial contraction pi from X to X2 with the exceptional divisor E mapping to a curve. Okay. And we know by the previous lemma, as I just mentioned, the downstairs the singularities will not be worse, okay, will be better than X. So this X2 is still a Q factorial Gorenstein threefold with isolated canonical singularities. And then we discuss the case X for X2. Okay, so if X2 has a final contraction or divisorial contraction to a point, then by some easy calculation on the extremal ray, we can show our original Kx plus TLX is ample. Okay, then also if X2 admits a divisorial contraction mapping the new exceptional divisor E2 to a curve, so there are two divisorial contraction X to X2 and X2 to X3. Okay, so if the second divisorial contraction the exceptional divisor has non-empty intersection with the curve, the image of the first exceptional divisor. Okay, so the first exceptional divisor is mapped to a curve on x2, right? And x2 to x3, there is another exceptional divisor, E2. So if this E2 intersection with this pi E is non-empty, then in this case, it will also be easy to calculate. So in this case, by some calculation, we can also show that kx plus TLX is ample. Okay, so finally, we construct a series of blowdowns. So from x to x2, x3 to xn. So inductively, we construct a series of blowdowns along disjoint curves. Okay, so we just in every step, it is a divisor contraction mapping the exceptional divisor E to a curve. And also, we may assume this curve has no intersection with the previous exceptional divisors. So then finally, our xn, since our x is uniruled, so finally our xn admits a final contraction to y. And also, if y is a curve, then it will be easy. Okay, so we may assume y is a surface. Then we are done by the previous conic bundle lemma. Okay. Note that in the previous conic bundle lemma, we require there is a linear combination akx plus blx is a pullback of an effective divisor from y, right? So this is another technical point. So in this case, we need to construct a linear combination D such that every contraction is D trivial, so that it is a pullback of some effective divisor from y. Okay. So as a conclusion, we are able to show the uniruled case. Okay. So in this case, if X is a Q factorial Gorenstein normal projective uniruled threefold with isolated canonical singularities, then we can show Kx plus TLX is ample for sufficient large T. Okay. So I think the uniruled case is not very easy to deal with, because we spent much time to consider the every step of the minimum model program. Okay, you need to consider the intersection of the curve and the exceptional divisor. Okay, so now we will end up the talk with some open questions. Okay, so first I will want to a question about the fourfold case. Okay, according to the paper by a paper by Haidong Liu and Matsumura, they show that the threefold case is not very. The remaining case is quite difficult, so they would like to go into the fourfold case. Okay, so parallelly, in our weak-Calabi fourfold case, we want to know whether this Lx is ample or not. Okay. So compared with the smooth case, which is almost solved by Liu and Matsumura, the remaining case, the numerical dimension equal to 2, and the Lx power 4 equal to 0, and the C2x times Lx square equal to 0. This case is very challenging. They are not able to show this case in this fourfold case. Okay. And also in our singular case, another very difficult part is the generalized Riemann-Roch formula. Okay, so this part is not very easy to deduce according to my consideration. And another question is, in the general case, when X is only assumed to be KLT, can we prove Cyrano's conjecture by running the generalized minimum model program? So in this case, we just, except for this X delta, we add another Neff divisor L, and we run the generalized minimum model program. And I'm not sure whether we can, by running this GMMP, we can have the Q effectiveness of the end product K plus delta plus L. Okay, so this is just to prove the Q effectiveness, and we note that the Jing Junhan and Wenfei Liu, the joint paper, and another paper by Lezik and Peter Neil, they obtain some inspiring results on this topic without assuming the strict deafness. But they usually assume this kx is pseudo-effective, but here we don't have such condition. Okay, so I think I will stop here. Thank you for your attention. Hi Shen, I think you don't open your.
Sorry. Okay, thank you very much for the very nice talk, very detailed talk. Okay, I think I learned a lot. And any question? Jaja or Park? Okay. Okay, I have one question in your question one. Okay.
Oh, yeah.
Okay, we can still discuss mostly on the Calabria case, but I guess your question one is still open in three-dimensional case, right?
Yeah, even in three, because they told me that the three-fold case is very.
I guess it is
difficult.
still too early to say to consider the Calabria four-fold case. Maybe too early. So still need the three-fold case, and this is what Opiso mentioned to me once before.
I see, because they tell me the three-fold case according to the previous the tours they told me it seems impossible to finish this case, so they just let it alone and go into the four-fold case. So but I think it should be more it should be better to first settle down the three-fold case. Yeah, for the four-fold case, they only give some partial results.
I guess there are many very small conditions in your assumption, your singularities, like a Gorenstein and KRT.
Yeah. The Gorenstein condition is only assumed when we run the minimum model program. So it is only assumed if we consider the unirule case. In the previous case, we don't need the Gorenstein case, the Gorenstein condition. Yeah, because actually I spent much time to deal with the flipping contraction, but on the flipping contractions, there are some technical problems for me. Yeah. So finally, I just added this condition to avoid the Gorenstein, to avoid the appearance of flipping contractions. Yeah.
How to say? Maybe sometimes flipping contraction is easy to consider because you construct the curve to a point, right? You just mentioned if you contract the divisor to a point, then it is easy, right?
Yeah, it's easy. Yeah, it's easy.
But if you contract the curve to a point, you don't know.
Yeah.
Because
I think there is no exceptional divisor, so the calculation, and also
and for small contractions, the cone changes a bit.
Yeah. Yeah.
Okay. Any other question? Okay. If no, let's thank the speaker again, and I will stop the recording. Okay.